Welcome to the module on applications of recycled batteries. In this module, we'll explore the essential steps involved in preparing spent batteries for recycling. Batteries are classified as primary or secondary, depending on their ability to be recharged. Primary batteries, or disposable types, are single-use and valued for their long shelf life and portability, making them ideal for low-power devices like remotes, clocks, toys, and hearing aids. Common examples include alkaline, zinc carbon, and lithium primary batteries. Secondary batteries, or rechargeable types, can be reused multiple times and are essential for high-energy applications such as electric vehicles, portable electronics, and energy storage systems. These include lead-acid, nickel-cadmium, nickel-metal hydride, and lithium-ion batteries, supporting the shift toward a sustainable, electrified future. Batteries power modern technologies from electronics to electric vehicles and energy storage systems. Yet, their growing use brings environmental and resource challenges. Effective recycling is essential to recover valuable materials like lithium, cobalt, nickel, and manganese, reducing waste and dependence on raw mining. Battery recycling supports a circular economy, lowering production costs, preventing pollution, and conserving resources. However, widespread adoption remains limited by technological and economic barriers. Advancing recycling systems is key to achieving a sustainable and resource-efficient energy future. Recycling technologies are vital for managing battery waste sustainably and recovering valuable materials. As rechargeable batteries, such as nickel-cadmium, nickel-metal hydride, and lithium-ion, become more widespread in electronics and electric vehicles, the number reaching end of life continues to rise, creating environmental and resource challenges. Recycling helps recover critical metals like nickel, manganese, cobalt, and lithium, reducing waste, cutting reliance on mining, and supporting a circular battery economy. These recovered materials can be reused in new battery production, closing the loop in the value chain. Further innovation is needed to improve the recovery of other components, including graphite, electrolytes, and plastic separators, to achieve a more sustainable and resource-efficient energy future. The battery life cycle begins with mining and refining raw materials, which are processed into compounds used in battery manufacturing. After production, batteries enter their use phase in applications such as electric vehicles, consumer electronics, and energy storage. At the end of their life, batteries may undergo pre-processing to separate components or enter recycling processes like pyrometallurgy, hydrometallurgy, or direct recycling to recover metals such as lithium, nickel, and cobalt. Some are repurposed for second life uses, such as stationary energy storage, before full recycling. Batteries that cannot be reused are sent for controlled disposal, though this is the least preferred option. The circular loops in the life cycle highlight how recycling and reuse help reduce waste, conserve resources, and support a circular economy, minimizing pollution and dependence on raw material extraction. Before recycling or disposal, spent batteries must undergo pre-treatment to separate their components safely and efficiently. This process enhances material recovery, lowers energy consumption, and reduces environmental risks during recycling. Pre-treatment also addresses major safety hazards, including electrical shocks, fire or explosion risks, and chemical exposure, which increase with higher battery energy densities. Key pre-treatment steps include sorting, discharging, dismantling, mechanical treatment, sieving, separation, and thermal or chemical processing. These operations ensure safe handling and prepare materials for efficient recovery in later stages. Together, they establish the foundation for a safe, effective, and sustainable battery recycling system. Recycling facilities handle a wide range of battery chemistries, making sorting a critical step for effective management of different battery types, sizes, and materials. Proper sorting helps address non-battery waste and ensures compliance with the specific requirements of each recycling plant. Early classification improves recycling efficiency by aligning processes with the chemical composition of batteries, which enhances product quality, minimizes losses of non-recyclable materials, and supports cost-effective operations. Additionally, accurate categorization helps accommodate equipment limitations and maintain safety during battery deactivation. Used batteries have permanently lost their capacity, but they still contain residual energy that poses serious safety risks, such as fire or explosion during transportation or disassembly. To prevent these hazards, it is crucial to fully discharge the batteries before any further processing. This step safely removes the remaining energy, stabilizes the batteries, and ensures safer and more efficient handling during subsequent disassembly and recycling stages. After the discharge of retired batteries is completed, the batteries must be disassembled to extract different components for sorting and disposal, which is an important step in the recycling process to ensure that the various components can be properly sorted and recycled. Unfortunately, there is also a large amount of toxic and flammable organic electrolyte in the waste batteries, and the improper operation during battery disassembly may cause short-circuiting of the battery and fire. After discharging and disassembly, the separated battery cells are processed through shredding or crushing to reduce their size. This step takes place under controlled, inert conditions to prevent ignition or explosion from residual energy. The shredding process breaks the cells into smaller fragments, producing a mixture known as black mass. This black mass contains valuable metals such as lithium, cobalt, nickel, and manganese, which are essential for new battery production. In addition to black mass, the process generates other byproducts including plastics, aluminum, and copper foils, which can also be recovered and reused. Overall, shredding and crushing are vital for preparing battery materials for subsequent separation and refinement processes, making recycling safer and more efficient. After shredding or crushing, the mixed materials from used batteries must be separated and classified to isolate valuable components. This step uses mechanical or physical methods, such as magnetic separation, sieving, and density sorting, to divide materials based on their physical properties. Through this process, materials are grouped into three main categories: magnetic materials, active materials, and non-magnetic materials. These methods improve the purity and recovery efficiency of valuable elements like lithium, cobalt, and nickel, while also enabling the proper recycling of non-metallic components. Separation and classification are essential for ensuring that each material stream is ready for the next stage, thermal or chemical pretreatment. The final stage of pretreatment prepares the materials for advanced recovery methods like hydrometallurgy or pyrometallurgy. Thermal pretreatment involves heating the shredded and separated battery materials to remove organic binders, electrolytes, and carbon coatings. This process helps make the materials cleaner and easier to handle in later stages. It also improves the efficiency and safety of the subsequent recovery steps. Chemical pretreatment, such as acid leaching or solvent washing, further purifies the materials by dissolving impurities and separating valuable metals. This ensures that the recovered materials, especially lithium, cobalt, nickel, and manganese, are ready for efficient metal extraction. Together, thermal and chemical pretreatment are crucial steps in optimizing recovery efficiency, reducing contamination, and preparing high-purity materials for recycling into new batteries. Batteries are essential for powering modern technologies, from consumer electronics to electric vehicles and energy storage systems. They are classified into primary, disposable, and secondary, rechargeable types, with secondary batteries driving the shift towards sustainable energy solutions. As global battery use grows, recycling is vital to manage waste, conserve resources, and recover valuable materials like lithium, cobalt, nickel, and manganese. Through pretreatment processes, including collection, sorting, discharging, dismantling, shredding, and chemical or thermal treatment, batteries are safely prepared for material recovery. Advancing recycling technologies and circular economy practices is key to reducing environmental impact, minimizing reliance on raw materials, and achieving a sustainable, resource-efficient energy future. Thank you for your attention.